Okay, in this problem says the blades of a wind turbine are 30 meters in length and rotate at a maximum rate of 20 revolutions per minute. If the blades are 6,000 kgs, so 6,000 kgs is roughly the weight of a school bus, let's say. So each blade, 30 meters is diagonally from the diagonal length of this room. So each blade is that much and weighs roughly as much as a bus. It has 3 blades. Calculate the angular momentum of the turbine at this rotation rate. Okay, omega is given to be 20 revolutions per minute. It's 20 into 2 pi radians divided by 60 seconds. So omega is 2.1 radians per second. 2.1 radian is about 120 degrees. And since it has 3 blades, in 1 second this blade gets there. Okay, so that's the rate at which it's rotating. Okay. And then we have to calculate the angular momentum. We have to calculate the moment of inertia. So we'll treat this as a uniform rod. Not true, because the blade is heavier near the axis and it gets thinner and thinner at the top. But for 10 bucks we can't do better than that. Okay, so we'll assume it to be a uniform rod. Calculate the moment of inertia of each rod about its end, and then you have 3 of those rods. Okay, so I'll give you the formula. This moment of inertia is given by 1/3 ml squared. Okay, and so for the windmill, it's 3 times 1/3 ml squared, and the mass is 6,000 kg for each blade, and it's 30 meters squared. Okay, so that's 954 into 10 to the 5 kg meters. Okay. All right, so now we calculate L. Let's go to a new page. L is I omega. And omega was 2.1 radians per second. Okay, so there's the angular momentum. Okay, so now they ask you, by the way, so what a windmill does is, so here's a very interesting fact. So here's the wind blowing, and what it's doing is, yes, so the wind has air as light, but it still has kinetic energy, so it's converting that kinetic energy into electricity. that the kinetic energy of the wind is converted into the kinetic energy of the fan, which is converted to electricity. The limit is, if there's wind blowing like that, you can in principle you can grab 60% of that energy. In practice, you get only about 40%. So 40% of the wind's energy is the fan is able to capture that. And then conversion to electricity is 90% efficient. So if you have a wind blowing, you know, 40% of that energy can be converted to electricity. Yep. Yeah, one that's all right. So moment of inertia. Okay, you guys can look this up, but this moment of inertia is 1/12 ml squared. This moment of inertia is 1/3 ml squared. Okay. This moment of inertia is bigger than that because more mass is away from the axis of rotation. I make mistakes all the time. Okay, I'm right 5% of the time and wrong 90% of the time. Even there, that didn't add up to 100%. Yeah. That was deliberate. Yeah. All right. So now they ask you, what is the torque required to rotate the blades up to a maximum rotation rate in 5 minutes? So let's say the wind started blowing and it went from 0 to 20 revolutions per minute over a period of 5 minutes. What was the torque that the wind exerted on the blades? That's the question. Yeah. And of course, torque is I times alpha, so we have to find alpha. And the final angular velocity was 2.1 radians per second. And this 7. So started off at rest. Alpha is omega by t, 2.1 radians per second, divided by 5 minutes is 300 seconds. Yep. So the torque the wind applied on this windmill was 5.4 into 10 to the power 6 kg meter square. All right, now let's try and make sense of this. So here's the blade. So just to give you guys, and the torque would be, let's say just for argument's sake, the wind is applying a force perpendicular there, and torque would be 3 times that force times this distance, which is 30 meters. Okay. So we have 37.8. So 37.8 times 10 to the 3 equal to 3 times that force times 30 meters. Okay. So this will just give you a sense for this. So I mean, so the 30 cancels with that, divided by 3. The force is 330 newtons. So it's roughly, okay, let me, the force is 420 newtons. So 420 newtons is roughly the weight of a person. So it's like a person is hanging on there and 3 people are hanging on there and they're rotating the plate. So that's the kind of force that the wind is exerting on it. All right. All right, guys. Is there any other parts to it? Yeah, no. All right.